Hi, folks. Good afternoon. Welcome back. Today, our lecture topic is most of the image processing lecture. We started just a bit of this, or the initial part of this last lecture, with the case study of JPEG compression. So let me just briefly remind you about what we talked about as a warm-up into the remainder of lecture today. So there were some big ideas in JPEG compression. And one of the big themes was talking about characteristics of the human visual system that were exploited in this JPEG compression standard. For example, that we were much more sensitive to detail in luminance or the brightness or darkness of objects or parts of the scene rather than the chromaticity or the coloration, right? And I showed some examples of this where we could take out detail in the luminance channel and it looked terrible, or we could take out lots of detail in the chrominance channel and it was pretty hard to tell that was happening unless you looked extremely closely at the details, and that this fact was exploited in JPEG for how they compressed out or reduced the resolution of the data set to reduce the file sizes by compressing the chroma space rather than the luma space. And we talked about how, as human beings, we're less sensitive to artifacts or less sensitive to error or numerical error in high frequency detail rather than low frequency detail. And this was also exploited in JPEG by applying a discrete cosine transform, essentially to move into frequency space. And then I talked about the details of quantization to keep detail in the low frequency portions of these frequencies rather than the high frequency portions through this quantization matrix approach. And I showed you some examples of the kinds of quantization artifacts that occur when you have higher levels of compression. And I told you about some of the final details and how this was laid out. This is some of the sort of mechanical details, the details of which were a little bit further from the theme of this part of the lecture, but exploiting characteristics of the human visual system, but still important. So run length, reordered values, run length encoding, particularly important for run length encoding, the zeros, Huffman encoding, and so on and so forth. Okay, so this is the compression summary. And again, the big theme here was exploiting perception in visual computing. We're perceptually insensitive to color errors, so we separate luminance from chrominance and compress the chrominance. We're less perceptually sensitive to high frequency error. That's a high frequency error in a spatial frequency sense. So we use a frequency-based encoding, cosine transform, and compress the high frequency values. And then one thing that wasn't covered in this lecture, but is another example in the JPEG standard of exploiting characteristics of human visual perception or the human visual system, is that we perceive lightness non-linearly. So increases linearly in a linear sense of power, and lightness would not be perceived as linear steps of lightness change for a human, speaking perceptually. And linear perceptual steps of lightness are much better matched to a gamma curve, gamma of about to a power of 2.43. We actually talked about that earlier in some of the color lectures. And so that's also encoded in the JPEG computing standard with a gamma curve that sort of that bends nonlinearly this conversion of lightness value in the stored data file compared to the value of lightness that will be displayed physically on a display. Okay, so that again sort of wraps up this JPEG compression. Again, the theme of exploiting visual perception characteristics for this standard. The reason I wanted to re-emphasize some of these big ideas is that when we talk about some topics in virtual reality in some upcoming lectures, this theme about exploiting characteristics of the human visual system is going to come back in a much stronger form. A lot of things in VR that are engineered in particular ways are engineered because we need to take advantage of characteristics of the human visual system to make the engineering practical. Okay, in JPEG compression, you could think of that as in a certain way when we're emerging with images or with the early internet, the file sizes involved in representing images was really a really big taxing. It took a lot of bits, right, relative to what we were capable of, and that's why compression was so important to enable these to take off, these image standards to take off, and we wouldn't have been able to do it without exploiting these aspects of perception. Okay, so that's a recap of image compression, JPEG image compression. This lecture is about image processing in general. So the next topic I want to talk about is to review some basic image processing operations, or to introduce them, or rather, if you haven't been exposed to this before. I think some of these operations we're very familiar with visually because of the kind of consumer applications in image processing that we all have access to these days. So here's some example image processing operations. Okay, so here's a blurring operation. Take an image of the Golden Gate Bridge, pass it through some image processing module that's going to result in a blurred image of the bridge. We could go the other way. We could pass it through an image processing module that will result in a sharpened version of the bridge. So if you look closely, you can see that the wires holding up the bridge are in much sharper visual relief compared to the sky. If you look in the tower of the bridge, you can see a lot more detail here, for example, as compared to the original image. This is a different version, something that is not, makes it no longer look like a photorealistic image, but rather is designed to draw out the edges in this scene is an image processing operation. So on the left-hand side, some kind of mechanical or some kind of physical mechanical device. And on the right-hand side, where all the edges in the original image, the boundaries between different parts of the image components are now highlighted in white, right? And the rest of the image is in black. This is an example of a quote unquote smarter blur. We'll talk about the mathematics of this and how it's implemented later in this lecture. But for now, you can see that this blur, unlike the example I showed before, if I go back to it just for a moment, in this example, right, this one, everything in the scene got blurred at the same time. So all the detail, for example, in the wires is gone, as well as the detail inside of the bridge tower itself. In this example over here, something slightly different has happened. It's definitely blurrier when you look at it in large parts of the image. For example, in the green, there's less detail in the leaves, and inside these petals, if you look inside, the detail inside the petals has been blurred out. But if you notice, the image edges, or the most salient image edges, have been preserved. So for example, between this blossom and the background, we have a sharp image, or a sharp edge rather, a crisp edge that's been retained. And similarly between this petal and the petals behind it. Okay, so this is a quote unquote smarter blur that is blurring between inside object boundaries, but preserving the edges between object boundaries as a goal. You can apply that, for example, in like a denoising application. So here's an example of a photo of a silhouette of someone against kind of an evening sky. In a zoom in of this portion of the original image, you can see there's a lot of noise. We talked in image sensors about where that comes from, right? That could be device noise from the image sensor itself as read noise, or dark current noise, or any of the other kind of sources of noise from the sensor level that we discussed. Or even if the sensor were incredibly high quality in terms of being low noise, we would still have noise from the signal of the photons themselves, right? Because of the statistics of photon arrival, shot noise or Poisson noise. These are all the synonyms that we use. So that's why we have this kind of graininess. If you apply that quote unquote smart blur from the previous slide, we could aim to blur out all of this detail, which in this case is grain from the finite SNR, signal to noise ratio, of this background. You could aim to blur it out, which would give perhaps a more accurate rendition of the background color, or inside the silhouette itself, but preserve the sharpness of the silhouette. Okay, so that's an example application. So a lot of these image processing operations can, of course, be modeled as convolution. Not all of them, not like the smarter blur. It turns out not even that edge detector that I showed you. That one involves a little bit of derived functions on top of convolution, as I'll show as we go through. But many of those can be represented by convolution. And convolution is a method to separate the filter on an image from the, or on top of a signal from the input signal itself. So to review convolution, which we've looked at earlier in the course in the section on aliasing and anti-aliasing and sampling, let's say that we have a convolution. So we have two functions here, f and g. Then the convolution of f and g, written in this form, f star g, at a position x is equal to this form that we've looked at before. So in this case, we could have the filter f of y with this auxiliary value, integration auxiliary value, a variable here. So integrating over dy, and then multiply it against the input signal g, but at a position x minus y, okay? For example, we could convolve with a box function where f of x, the filter, is 0 everywhere except being 1 near the origin between negative 0.5 and 0.5. So a box function like looks here, as it looks here, right? So we could have f convolve with g, where g is some input 1D function. And if you substitute it into this equation up here, then we can note that because f of y is only, in this particular case, 0 between negative half and half, this form of this equation can be simplified down to the thing here, which would be to integrate from negative 0.5 to 0.5 g of x minus y dy. Okay. And so the output in this case, f convolve with g, would be a smooth version of g. It will be g convolve with this moving average of this box function. And the g that results, of course, is, so the f convolve with the g that results, of course, is g, but where at every point in the output x, we're replacing g with the integral of g over a box from negative half to half at that x value, minus half to plus half at that location. This is a little visual diagram of an example of it. So if f were itself, g were itself, in this case, a box function, then convolving it with a box function can be visualized as this animation of moving the filter, or in this case, moving the function g, the red, and sliding it across the filter, and the result, if you integrate it, would be this triangle function here. That was in the 1D case. Of course, for all the image processing cases examples I showed earlier, we're operating in the 2D domain, right, of images. So there's a corresponding version of this for 2D convolution. And in this case, I've also shown it in discrete form rather than the continuous form. So if we have an input signal I, where I of xy is the input image, I being that function of the input image, and f still being a filter, but in this case, f is a 2D filter of f of xy, or in discrete form, f of ij. Then the convolution f convolve with I at any position that we care about xi would be the integral over ij, ranging over all positions from negative infinity to infinity for each of ij, where we multiply the filter f of ij times the image I at position x minus I times y minus j. So this is a direct 2D extension of the 1D case that I described just before. And although it's written in this form, in the general case, 2D convolution can be over a filter that is arbitrarily large. For all real image processing examples, we, of course, can't have infinite extent filters or images. We have finite size images, and in general, we have filters that are much smaller than the input image. This is for computational efficiency reasons that we'll see in a little bit more detail as we kind of go through. So, but f of ij is usually non-zero only for some very finite set of values. One of the most extreme small versions of a filter will be one where ij both lie between -1 and 1. And if we're in integer space, then there'll be just values -1, 0, and 1. In that case, for that example, then f convolved with g, where g indicate, oops, this is a typo, should be f convolved with I. At positions xy would be just for ij running from an integer space from -1 to 1. So just 3 values each, 9 values altogether for I, for the cross of I and j, in this form, f of ij times I of x minus I, y minus j. Okay, someone wrote y is the input signal g of x minus y. In this case, it's not. There's a typo here. This g should be an I. Someone asked, does Monte Carlo integration work with convolution? That's a great question. And you could, if you used, let me sort of back that up for a second to address this interesting question that Justin asked. So could you use Monte Carlo integration with convolution? And I think that it's a bit clearer that the answer to Justin's question very much could be yes, in the continuous case that I showed for the 1D version here. In moving to the 2D version, I already went to a discrete form, okay, where we're operating on a lattice, a discrete lattice. And in this case, it's because we're going to be operating with images that are defined at grid positions only, integer grid positions, and also we'll consider filters that are similarly discretely sampled. So this could be thought of like similar to the raster, the discrete raster positions that we looked at in rasterization or for ray tracing. So that kind of image representation. However, you could imagine also, and there are mathematically speaking, convolutions that are defined continuously here. So integrals, 2D integrals for f of ij, and then integrate over the 2D domain continuously. In that case, then you could interpret, you would see that this 2D convolution in the continuous domain would be just a 2D integral. And in that case, you could definitely apply Monte Carlo integration in order to try to evaluate that. That might be more common in maybe scientific applications where you might model, problems with 2D convolution in that continuous domain. For image processing, though, it's very uncommon. For image processing, what I'm showing here is the way that it's done in practice, okay, which is discrete and with discrete sized convolution filter kernels. So for this example here as the canonical example. Okay, so here only for the filter that's 3 by 3 wide, okay, if it's -1, 0, 1 for each of ij, then the overall 2D filter in this case is 3 by 3. And so this here would represent an integral over a 3 by 3 values. And which is what I said here. So f of ij would be a 3 by 3 set of values, which you could represent as a matrix as an example. And these values are often called the filter weights or the kernel. You're welcome, Justin. Good question. So here's a simple example of a 3 by 3 box blur. Okay, it's a bit of code. Let's take a look at it together. So one caveat I just want to note here is that you can conceptualize what we're going through, what this code is doing is taking in an image, okay? In this case, width by height pixels. So picture it, as like a high resolution image, and then we're going to blur it by this box blur, which is a 3 by 3 wide filter kernel, as I described on the previous slide. There's one caveat here, which is that there's subtleties in sort of the details of how you implement this. And in this case, we're going to assume that the input is width plus 2 pixels times height plus 2 pixels, and the output is width times height to ignore the boundary pixel conditions. Because if you have a filter that is 3 by 3 wide and you want to do the leftmost pixel in an input image, then you might need a pixel that theoretically is off the end of the left edge of the image, and vice versa for the right edge. You might need pixels that are off the right edge. And there are ways to modify the boundary conditions so that the filter kernel is clipped, for example. There's different choices you can make so that the output image you get is the same resolution as the input image. It is a lot simpler, though, to handle the indexing and to not have to define the changes in the filter weights for those kind of boundary conditions by taking the approach that's shown in this simplified pseudocode or simplified code here, we'll ignore the boundary conditions by assuming the output image is slightly smaller than the input, as is done here, okay? All right, so the input image being width plus 2 times height plus 2, the output image is going to be width by height. This is an array here that represents the kernel itself. The weights are 1 over 9. They're all the same. Okay, so it's a flat box function in 2D, defining this box filter blur, but it's over 9 so that it's normalized. Okay, so because there's 9 values in here. The effect of this would be so that, for example, if you're in a constant part of the image, what's going to happen, you're going to sum up 9 pixel values. If you didn't divide by 9 or have it be 1 over 9 here, then the output image would be brighter, right? Then it would be 9 times brighter on average than the input image. So this is just a normalization. Jake asks, why do the weights array and not just take the average? I'm not quite sure what the, maybe clarify the question, Jake, if I didn't cover it already with my explanation here. Okay, so what does this kernel look like? It's not very complicated. Let's just go over it. Okay, so we integrate over all the image pixels. So we integrate over I and j, for I running from 0 up to width minus 1, and similarly for j up to height minus 1. Okay, so we just enumerate over all pixels in the image. Then what we do is we calculate a sum of the internal filter kernel. Okay, so we compute a sum that is runs, in this case, JJ and II, which are going to run over these filter weights. So you can see they run from 0 up to 2, 0, 1, and 2. We calculate a running sum, which we initialize the running sum temp value to 0, and then we increment at each one of these iterations here. We integrate over, integrate over what? We integrate over the input pixel values centered at position J, and then adding JJ, this running index over the filter kernel indices. And so this is the the value in the input for the Y value, conceptually the vertical value, and then the horizontal value. And we, at each case, get the value in the input image, and then we weight it by the filter kernel values in this weight function over here. Okay, so for the corresponding JJ and II coordinate in this 2D filter array. After that, we set the output image value at the corresponding value of J. So J times width plus I is going to be this running weighted sum. Okay, so that's it. We just calculated this weighted sum exactly according to the summation mathematically defined on the previous slide. I see the question that Jake asked. Yeah, Jake asked, why not just average by 9 or normalize by 9 at the end instead of getting the 1/9 from the array? You're right, we could totally do that. But if we capture it all in the weights, then mathematically we won't have to insert this division by 9 later and sort of, well, where's that 9 coming from? We could do that too, sort of insert a normalization function here, but in this case, the normalization has been baked into the weights of the array. That's all. Mathematically, it'd be the same. Okay, so that's an example of looking at the implementation of a 3x3 box blur. To demystify it, okay, there's nothing very crazy going on in this convolution. It's, as you can see, iterating over the images of the pixel, and then inside the inner loop, iterating over the values in the 2D filter array, and then forming a weighted sum of every pixel. One thing you should note here is that, convolution is kind of an expensive operation when implemented in this way with a general filter kernel here. In this case, we got to perform 9 summations, right? We've got to sum up 9 values inside the inner loop while iterating over every pixel of the image. This is for a pretty small kernel of 3x3. If this could get large, you could have a filter kernel that's 10x10 or larger. Okay, so we'll go through that, the complexity a little bit, but the high level thing that you can note here is that convolution can get pretty expensive computationally pretty quickly. Let's look at some examples. Here is a 7x7 box blur. Okay, so this example original image here is a texture of a brick pattern. There's a zoom in of it on the right-hand side. And then blurred with this 7x7 kernel. This is the output here. Okay, so you can see there's a significant loss in detail. On the right-hand side, you can see all the sort of grouting detail is blurred out. You can have different values inside the filter kernel, of course. It doesn't have to be this box function that's a constant over all values. Here's an example of a Gaussian blur. So we can obtain the filter coefficients inside the filter matrix by sampling, for example, a 2D Gaussian. So here's a Gaussian, the formula for a 2D Gaussian addressed in 2D space by positions I and j. And this would produce a weighted sum of neighboring pixels where the contribution falls off with distance, exactly like a Gaussian function, like a bell curve, right? Now, since we're discretized, for example, if we tried to have a 3x3 sampling of a Gaussian blur, then there's going to be some significant deviation between a smooth 2D Gaussian function that you might picture continuously and our discrete approximation of it, because we'll have to truncate the filter beyond a certain distance, right? So in this case, you can see the maximum value in the center is 0.204, and then it decreases to 0.075 in the corners, but only to 0.124 on this position here. You could, of course, have a higher resolution version of this Gaussian blur, which would be a higher resolution discrete Gaussian blur. For example, you could have a 7x7 version of it, okay? That was 7x7 pixels wide in the filter. This is what you would get, okay? So here's the original image again, in this case, blurred by 7x7 Gaussian blurs in the bottom. So you can see it's still really blurry, and over here too. It's interesting actually to compare the 7x7 box blur, again, which I just bring back up here. I showed it to you before, so this is just bringing it back against the Gaussian blur. So if you look at the bottom, you might notice two things. Obviously, both are blurrier, okay, than the input image. But one thing you might kind of note is that there's some sort of residual artifacting, if you will, going on in the 7x7 box blur. You can see it here, actually. You might notice there's some sort of brighter sort of strips that sort of remain, whereas it looks maybe a little bit smoother, blurrier, but sort of a smoother blur in the Gaussian case. And actually, this is no accident. There's a way to analyze this in terms of the spatial frequencies and the spatial frequency content of this filter function. You could think of it as taking the Fourier transform of this filter kernel, okay, as we discussed in the anti-aliasing lecture. And what you could sort of imagine from just purely from intuition from the anti-aliasing lecture is that if you had a function like a box function in 2D, okay, so the box function like the box blur here, it's a function that has very high spatial frequencies, right? Because it has a sharp corner at the top, right? It goes from a flat value down to 0 instantaneously. And that very rapid change in function value, remember, rapid change in signals. In this case, the filter here is the signal that we're going to use for filtering our image against. That box blur has a very sharp transition, which means that it has very high spatial frequencies. Whereas the Gaussian function, because it rolls off smoothly, right? Smoother variation, slower variation means lower spatial frequencies overall. And that means that it's less prone to aliasing. And in fact, the 7x7 box blur is some small amount of residual aliasing that is carrying through in this convolution. I got a question, a direct question that's a really good one. So someone asks, how would a 7x7 blur compare to, for example, 2 3x3 blurs applied sequentially? That's a great question, and one actually that you can analyze completely mathematically, okay, based on just the things that we talked about. Let me talk about it a little bit intuitively first, okay? So the 7x7 box blur results in averaging, every 7x7 block, 7x7 neighboring pixels to calculate an output pixel value at the corresponding location in the output image. So it's going to blur more than if we run just one 3x3 box blur, because if we ran one 3x3 box blur, we'd only average 3x3 neighboring values, right? But if we run a 3x3 box blur once, and then we run it again, you can see that the output image pixel is going to gather contributions from, let me think about this a little bit. It'll be 3, and then another 3 on that side, another 3 on that side. So I think it's going to be a total of 6. I have to think I think it's a 6 by 6 radius across, but it won't be a box blur anymore. You can convince yourself that the final output image value is not going to be a uniform sum over that entire spatial extent of the filter kernel, but it's going to be slightly weighted towards the center. In fact, if you reason all the way through, you can actually convince yourself mathematically that it'll be kind of like a triangle function, okay, a triangle peaked function. But yes, you can definitely iterate convolutions, sequentialize them, run them again and again, and you can consider the computational intensity of doing them in that form too. But convolution kernels are not just for blurring, okay, not just this box blur versus a Gaussian blur. We saw examples, for example, that can do lots of other things. So let's go through some of those examples. What does this convolution kernel do? It's 5 in the middle. Notice it's got a negative value on the horizontal and the vertical directions and 0 elsewhere, okay? But it's got a negative value in each of these locations. So maybe you could think for a moment and try to imagine what's going to happen when you run this filter kernel over the image, right? We're going to run it, this filter kernel, intuitively, you can think of it as you put it down and you sum all you form the weighted sum of these neighboring pixel values, and that becomes a value in the output image. Then you move it over to next location in the image, the same filter kernel, form that weighted sum of the input image pixels and write it to the output image. That's the right kind of picture you can have in mind. But would this do? Yeah, Gavin suggests, would this like sharpen the image or something? And yeah, that's exactly right. This image, this filter is going to sharpen the image. Let's take a look at it first and then sort of reason through what happens. Again, here's this example I've been using of this brick texture. This is the output after applying that filter kernel on the previous, okay? Why is this happening? One way to look at an example is that you can sort of think about what happens when this filter ends up right on an edge. When it's right on top of an edge, what happens is that, let's say pick this 1 pixel edge here as an example. Okay, it's a positive value. It's got the positive value, the 5 in the middle, and then it's going to subtract the pixel values to the left-hand side and the right-hand side. So when there's a movement in that edge, it's going to end up increasing. You can convince yourself it's going to end up increasing the magnitude of the change across that edge. That's what the effect of these negative values compared to a positive value in the center is going to do. And that's going to have an effect because it's both the negative values are both in the vertical and the horizontal direction. It's going to increase the size of that step, whether it's a horizontal for horizontal edges as well as vertical edges, where edges are defined by a large change in the pixel intensity value. Okay. So it's a sharpening example of a sharpening filter. And Drew asks, will this only sharpen 90-degree edges, right? Not all edges. And that's right. So if you had an edge that was purely diagonal, then this wouldn't pick it up. And you can convince yourself of that because there's these 0 values on those cross-diagonal terms. So if it was truly purely diagonal, then it would escape. What does convolution with these filters do? Okay. So this is one that has -1, -2, -1 over here, and 1, 2, 1 over here. And then this is just rotated. Okay, so -1, -2, -1 in this row, and 1, 2, 1 in the bottom over here. So what does this do? This is a little bit different than the previous example. And one of the ways you can tell that it's very different, okay, is that in the previous example, the average, right? Let me go back to that for a second. The average here is still 1, Okay, it's 5. If you sum up this filter kernel, what's the value? It's 5 minus 4. Okay, so it's still 1. So if you ran this, you're saying that basically I'm going to form a weighted sum that on average is going to be a weighted sum of 1 over every pixel. So it's going to maintain the average pixel value. That's why this looks as the average. On average, it's the same intensity values here. That's not going to be the case with these, right? Because the average filter value in these kernels is 0, right? It's a -1 + 1, -2 + 2, so on. So this is it's an average value of 0 everywhere. So what do these filter kernels do? This is going to extract horizontal gradients, and this is going to extract vertical gradients. Let's take a look at the output. Okay, so this is applying the horizontal gradient filter on that brick texture, and you can see what it's done. It's picked out all the values, all the locations in the grouting where there was a vertical feature, right? A vertical grouting feature. And this is the vertical gradients. It's picked out all of the horizontal edges in this scene. So there's a little note here. So this is an example that shows you can think of a filter as like a detector of a pattern. And the magnitude of a pixel in the output image is the quote unquote response of the filter to the region surrounding that output pixel in the corresponding pixel input image neighborhood. Okay, so if it's bright in this output image here, it means that in the input image, that same pixel location or the neighborhood of pixels around it responded a lot to that detection kernel. And the detection kernel in this case, in this bottom image, is a vertical gradient detection filter. Someone says, oh, maybe this is a Sobel filter to find the slope of the edge. So you can turn this into a Sobel edge detection filter by taking those two kernels I showed. Let's call that this filter kernel here. We're going to call the output image when it's convolved with an input image, right? This filter kernel convolved with I. We'll call it G sub X for the X, the horizontal gradients. And similarly, G sub Y for this filter kernel convolved with the input image. Here's a visualization of it. So on this example image that I showed earlier, so G sub X looks like this. It picks out all of the horizontal gradients, G sub Y, the vertical gradients. But if you look closely at these images, it's not kind of symmetric. Okay, it's not the same in both directions. So G, which would be the Sobel image, it can be formed from G sub X and G sub Y by combining them to keep the brightest image pixels in both. And a way to do that is shown here. So G can be equal to the pixel intensity in image G sub X squared plus G sub Y squared, and take this, the all squared magnitude of that. So this is an example of a pixel-wise operation on top of these images formed from convolution. Let's talk a bit more about the algorithmic costs of this convolution-based image processing. As I already noted, right, you can look at that sample code that I showed and note that the inner loop, right, of iterating over this image pixels might contain a lot of computation if that convolution kernel ends up being large. And if you're in this general case, right? So what's the cost of a convolution with an n by n filter? This is a reminder of that pseudocode that we looked at before for the 3x3 box filter. So in this case, it's something like, we got to do something like order n operations in the inner loop. 9 rather, order 9 operations in the inner loop, some pluses and minuses in the iteration arithmetic too, of course, bookkeeping, but 9 because the filter kernel in this case was 3x3. So in this 3x3 box splitter example, the total work per image was 9, proportional to 9 times width times height. For an n by n filter here, it's going to be, right, of course, n squared by width by height. So that's easy to see, which can get, as I described earlier, could get pretty expensive pretty quickly. In fact, for denoising filters, I'll give you an example. Denoising filters in early digital still cameras, they found practically that to denoise images reasonably, to make reasonably decent looking early digital photos, they needed kind of large filter kernels. The denoising filter might be like at a minimum 13 by 13. For image quality reasons, they might have wanted to go larger than that actually. But for engineering reasons, speed reasons, they might want to go smaller than that. And remember, in a digital still camera, it's kind of a hard spec because you click the picture, and then what's the first thing the person wants to do after that? They want to hit the play button to look at the picture they just took, right? So if you want to apply all your image processing immediately after the picture's taken, you have to run this kernel. And if it's a 13 by 13 denoising filter, you need to run all of those operations over, like say, a 10 megapixel or larger image, in a very short amount of time. So these are, the ASIC engineers that were responsible for implementing that would really debate on what size denoising filter they could afford. Is it 13 by 13, 11 by 11, 9 by 9? So these were the ways that those sort of played out in that case, okay? And because of that, they almost always went to cases where where they could make it separable. So this was a very important engineering optimization that was made very commonly. You can't always separate a convolution filter into two linear 1D filters, but in many cases you can. And if you can, it can be a lot more efficient. It's usually way more efficient to do that for a reasonably sized 2D convolution kernel. So here's an example. This 2D box blur function that we looked at before can be represented by two 1D kernels, a version that's vertical and then a version that's horizontal. Okay, so what does this mean? It means that if you take the input image, you convolve it with a 1D filter, which means that what does that mean mechanistically exactly? You take all the pixels in the input image, and then you slide this first, say the horizontal filter first. You slide the horizontal filter over every image pixel location, but you average only the 3 pixels in a line horizontally, not 9, just the 3 on that line. Then you generate an output image. You take that output image and then you blur vertically, right, with this vertical filter, and you average only the 3 pixel locations vertically over every location. Okay, so mechanistically, that's what's going on. It turns out the 2D Gaussian case that I showed you earlier can also be represented by two 1D Gaussians taken as sequentially, okay? So you can separate this filter, or this 2D Gaussian filter is a separable filter in the same sense. So a key property is that 2D convolution with a separable filter can be written as two 1D convolutions mathematically exactly, okay? And if you do that, then it's going to be a lot more efficient to run this to calculate it, okay? So in this case, this is a fast 2D box blur implemented via two 1D convolutions, okay, in opposition or in contrast to the example I showed before with the single 2D 3x3 box blur. So this is all just written out. This is, I won't go belabor the details because I already described intuitively what's happening. This is iterating over the image the first time and then integrating over just the horizontal 1D filter. So we're integrating over only II, which is the index for the filter in the horizontal direction. And then we run it or iterate over all those image pixels again. And in this case, we iterate over JJ for the vertical index location into the 1D vertical filter kernel. So there's a little bit more code to write than before, but this is more efficient than before as well. One thing you also notice is that we needed another temp buffer here to take the input image and then calculate a temporary image before calculating the output image. So what's the total work here per image? It's, in this case, something like 6 times the width times the height, right? Instead of 9 from before, 3 times the width height here and 3 times width times height here. And in general, for an n by n filter, they can be separated into two 1D n wide filters. The total work is 2n times width times height instead of n squared from before. So of course, in an asymptotic sense, this is a big win, right? Order n times the number of pixels versus n squared times the order times the number of pixels. So this can be a huge win computationally practically if you were to implement this. Okay, let me just sort of wrap up the talk here. So the extra cost of this approach, at least in this implementation, there's extra storage here. This is an interesting challenge. This is something that image processing engineers that implemented some of these early, for example, digital camera filtering operations, such as denoising, that use this approximation as a key, key optimization. There's separable filters. They also have to think about like, well, do you have to store all of the data at once, or what's the, are there more clever ways to do it? What is the minimum data that you can store in a working set, temporary working set, in order to optimize this? I'm not going to go through the details of that, but I just note that you can optimize this very significantly. So the challenge is, can you achieve this work complexity without incurring this cost or minimizing the storage cost? We go to some questions in the comments. Dhruv asked, are non-square filters also useful? Yeah, for sure. They absolutely can be. Anisotropic filters could be useful depending on your application. For example, if you're interested, as we looked at in cases where you're primarily interested in like finding horizontal edges or horizontal features, and you want to look a little further out to have more sophistication in your filter, you might have wider, like a horizontally wider filter as an example. But usually, I would say the more common case is for the filters to be symmetric in size, and X and Y is more common. Gavin asks, are the gradient filters separable? Seems like maybe they wouldn't be. Yeah, really great question. I think a good one to puzzle through. In that case, yeah, actually, I'm going to sort of leave that as an exercise to take a look at. The exact version that I showed, I think you're right, they're not separable, but could a close approximation be something that might be separable, or maybe even turn into a 1D filter? Might that be an engineering trade-off that might be worth doing? Something that might be interesting to look at. One last point, last couple of points. I have a couple of slides on this for, just a couple of slides, but these are big ideas. Relate to computing this convolution in the frequency domain. So recall from the sampling, aliasing, and anti-aliasing lecture, the convolution theorem that I showed you in visual form. Okay, so to remind you, in the spatial domain, you could take a convolution. Here's the one we just looked at. Okay, some kind of box blur as the filter here, an input image, and then calculate the convolution of this to get a box blurred image as the output. And of course, this is just an example here of a box blur. You could put any filter function that you wanted here. And in fact, if you had a large filter here, like so you had a really clever filter that you really wanted to put and had a wide extent, this spatial domain operation is going to get expensive. It's going to be equal to, in complexity, proportional in complexity to the footprint in pixels of this 2D filter kernel here, okay? So this represents spatial domain convolution implemented by the same kind of code I showed earlier, and with whatever filter kernel that you want here. The convolution theorem says, though, that you could take exactly this mathematical operation that you want to implement in the top line, and you could implement it in the bottom line in its terms of its spatial frequencies. So in the Fourier domain, right? So specifically, if you had, or you compute the Fourier transform of the image, the input image, and you compute the Fourier transform of the filter kernel, then you can get the Fourier transform of the output image here, this convolved image, by just taking a pixel by pixel multiplication of these two images here. That is a pixel by pixel multiplication of the Fourier transform of the image times the Fourier transform of the filter. Now, of course, if you did this in the frequency domain, then you have to transform back into the image domain, because you eventually probably care about seeing this image here, not just having this Fourier transform, okay? But let me just sort of lay that out. So you could compute two forward Fourier transforms, do a pixel by pixel multiply to get this image here, and then take one inverse Fourier transform to get back over here, okay? Now, you might say, okay, well, required, right? I believe you that mathematically you could do that, but that sort of seems like, you know, a lot more complicated than just doing this convolution operation that we had before, which is true in a certain way. However, just remember how the complexity of what we looked at here is, say, n squared pixels in the convolution kernel here, means that, let's say you had n squared pixels in the image, and let's say you had a very large convolution filter kernel. Let's say it was also n squared. Then the convolution in the spatial domain is an n to the fourth operation, right? Iterate over n squared pixels and then iterate over n squared filter filter kernel positions inside the inner loop. So that will be an O to the, of n to the fourth complexity operation here. Let's contrast that with what's going on in this other route that I described. Okay, so first thing is you have to perform Fourier transforms. Fast Fourier transforms, you may recall, we didn't talk about it in detail in this class, but it's a very famous fact, a very important engineering fact, that a fast Fourier transform is an n squared log n operation for images, n log n for 1D, n squared log n for 2D images or signals. So this operation here is an n squared log n operation, and this one here is an n squared log n operation. So you got to do 3 n squared log n operations, which is still O of n squared log n, okay? How about this multiplication here? Well, the great news is this part is super duper efficient, okay? Because it's a pixel by pixel multiplication. So you only need to iterate over the pixels once. And so this is O of n squared. So overall, implementing a convolution in the frequency domain is O of n squared log n complexity versus O of n to the fourth in the spatial domain if you had a really large filter kernel, okay? So usually if engineers are faced with implementing a convolution kernel in the spatial domain, and that's the code they're going to write, or that's the ASIC, okay, logic they're going to lay out, they will be forced to choose a very small filter kernel. If you want to run a large filter kernel, then that puts a very strong bias towards considering doing it in the frequency domain, okay? So what's the efficiency? I just walked it through then. When is it faster to implement a filter by convolution in the spatial domain? And when is it faster to implement a filter by multiplication in the frequency domain? There'll be a breaking point there. It'll come down to the size of the filter kernel. And at some point, for a filter kernel that's large enough, it will be faster to implement it in the frequency domain because of the asymptotics that I just reviewed, okay? Does the idea of separable filter extend to frequency domain? Is there any way to make it faster by separating? I really like this question. Thanks, David. I'd have to think a bit more about that. Yeah, I think there are 1D analogs to each of these things that I described. But actually, as I'm thinking about it a little bit, I mean, the win that you get from going into the frequency domain by enabling this point-by-point multiplication means that trying to do the separable trick, I think, is going to be the additional win you could get from that would be very constrained if you could win at all. It will all get subsumed basically by the cost of going to the frequency domain and coming back, which is this O of n squared log n Fourier and inverse Fourier transform. That's my sort of off the top of head sort of reaction or instinct on it. Does the frequency domain solution cause more floating point errors? Is a question that Alexander asked. That's a good question. It's generally not a problem, but you do have to have sufficient precision in going into the frequency domain, through this Fourier transform operation. So it's something it's a good consideration. But in general, frequency domain floating point error is not a problem that's a very common one, I wouldn't say. More generally, there are sort of boundary condition issues that do need to be taken care of pretty carefully to avoid what are amount to aliasing, or sometimes what's called post-aliasing or introduced computational aliasing problems in some of the boundary conditions of these functions that are shown here. So that's well beyond the sort of detail that we're going to cover in this class, but implementing this, which can be done, often requires some additional tricks and attention to detail in exactly how all of these are handled. But you can start to experiment these if you have interest in this on your own, directly using some packages to calculate the Fourier transforms and sort of see what happens. You'll see some of the visual artifacts that occur that occur if it's not handled in a careful way. Thanks for the great questions. Okay, let's move on to a next sort of class of, in this introduction to image processing, sort of this survey, let's move on to a next class of filtering operations or image processing operations that depend on, have a data dependency in the filter. Okay, so what's the simplest example of this? We can consider a median filter. Okay, so what's a median filter? Here's an original image. So what does a median filter do? Here's a 1 pixel median filter. Here's a 3 pixel median filter. Here's a 10 pixel median filter. You can tell it's performing something akin to, or visually akin to, a blurring operation. What is it doing? It's running some kind of filter that has a certain size. And then in this case, we're replacing the output image value is equal to the median value inside the filter neighborhood in the corresponding location in the original image. The pseudocode for this is really simple. Okay, here's the input and the output images. We just iterate over all pixels in the image, and then we set the output image pixel at position j times width plus height plus I equal to a little bit of code that I omitted here. Just put a comment and said just computing the median value of all the pixels in the surrounding, I guess in this case I've assumed it's a 5 by 5 pixel median. So the median pixel value in the 5 by 5 pixel of the original input image. Okay, and if you do that, you get these sort of outputs that you can see here. Now this is pretty different than the pixel or the weighted sum data filters that we looked at before in the previous filters, because you have to do something pretty sophisticated computationally inside the inner loop here to compute the median pixel value. I didn't write it because it takes a little bit more to show, but if you think about it for a second, to compute the median value out of 25 pixels, you have to sort them. Okay, so you gather all those 25 values, then you have to perform a sorting operation, and then you pick the centermost one. That's the median, right? So you can imagine how you can put sophisticated nonlinear image processing or nonlinear computations inside the inner loop of these filter operations, and in general, compute functions over the neighborhood of values in the filter kernel neighborhood on the input image, the median filter being one example, okay? Oftentimes that can get very powerful, but very computationally expensive very quickly. So people have tried to do different versions of this that provide levels of sophistication in the processing, more degrees of control that are valuable, but that are still relatively, relatively efficient to compute. One famous example of that is called the bilateral filter. This is that quote unquote smarter filter that I showed you earlier, okay? So again, this is another example. You can see as a reminder, the effect of this filter was that it averaged or blurred out detail within regions of the image that are, visually speaking, look like the same object. So in this case, in the skin of this person that's shown in this photo, but it did not blur across the edge here. So if you just ran a box blur or a Gaussian blur, then and you had it enough to cause this amount of averaging inside the skin area, it would cause a very blurry edge at this boundary here between the dark background and the forehead, right? So removing noise while preserving image edges is a classic application of a bilateral filter, as this thing is called. The intuition you can have is that, okay, this is thanks to my co-instructor last year, Professor Kanazawa. So you can think of filtering that's isotropic as like infusing tea in a cup. Okay, everything gets infused, all the liquid gets infused the same way. And anisotropic, or in this case, data-dependent filtering, is something that tries to separate different portions of the data that you're attempting to filter and treats each of those portions separately. Okay, so you kind of have distinct flavors in different regions of your hot pot soup, for example, that remain separated. So that's what the bilateral filter is attempting to do. And the separation that we're going to incorporate in this case is to prevent blurring across spatially or filtering spatially, we're going to modulate or control where we're allowed to modulate or to filter spatially by looking in another domain at the same time, which is going to be in intensity. Okay, so think of it as the bilateral, bi meaning two dimensions at the same time. One of those dimensions is spatial. That's the same as the convolution-based filtering we've been looking at. The other dimension is in intensity space. Okay, so let's take a look at how that works out. If we have an input image, I, and we're going to compute the bilateral filter of it, the bilateral filter has two kernels defined. One that's a G. Okay, this is like before I'd use F, little f, that's fine. In this case, think of it as a Gaussian blur kernel. Actually, you can put any filter kernel that you want here, but a very common use in bilateral filter is going to be blurring. And so we'll have a Gaussian blur kernel here, G of XY. And there's another filter kernel function, F here. And this F is acting on what? It's acting, let's take a look at this parameter value that's being sent in. It's being given a value that's equal to the difference between, for a particular IJ location in the filter support, and for an output location XY, right? So centered on an output location XY and offset from that XY location by IJ, it's going to take the intensity of the input image, so I of X minus I, comma Y minus J, and compare it to the center value. The intensity is XY. So it takes the center intensity value as sort of a reference. And then for all of the other potential pixel locations inside this filter domain, all the IJ locations, it looks at the intensity difference in the image at that location compared to the reference intensity at the center, and it passes it into this function F. So what F is going to do, or what F could do is, for example, if F was a Gaussian, it could say that if the intensity difference was very small, 0, for example, that it would be, F would be high. But if the intensity difference was large and we used a Gaussian for F as well, then it would be small. Okay, so if the intensity values are very different, F would be crushed down. And the weight that we apply, this again is computing a weighted sum of the pixel values inside the original image within this neighborhood, right? This filter kernel neighborhood. The weight now is why it's called bilateral. It's the product of these two terms here, these two factors, F and G. G is the one that we have all along from convolution. F is the factor coming from looking at the intensity difference. Okay, so if the intensity difference is really large and we had F being a Gaussian, then this would make the weight of that for that pixel become very small, even if G was large. Okay, so that was sort of an analysis of the defining equation. We're going to look at some pictures and some examples in a second, okay, to sort of try to build up our intuition about this. First, a couple of just points to anchor about this. So the value of the output pixel at position XY is the weighted sum of all pixels in the support region of that filter, of what you could think of as a truncated Gaussian kernel. I'll show you a picture of the truncation of that Gaussian kernel in a second. The weight is a combination of both the spatial distance away from the center of that region, as is the same in convolution, right? But it's also a function of the intensity difference, as I described. This is another example of a nonlinear data-dependent filter. The data in this case, meaning the intensity values in the picture. Okay, the value of the filter kernel weight is going to depend on that data. So the bilateral filter is an edge-preserving filter. Will downweight the contribution of pixels on the other side of a strong edge. Okay, an edge being a large change in intensity value, of course. We're going to downweight the contribution of pixels on the other side of a strong edge. F of X is going to define what strong edge means in a numerical sense for us. Okay. The spatial distance weight term F of X could itself be a Gaussian. That's what I mentioned already before in this example. But it could be other simpler functions too. For example, it could be a very simple threshold. It could be F of X is equal to 0 if X is greater than some threshold. So that would say that F of X just becomes 0, will downweight it completely if the intensity difference exceeds some a certain amount. Let's take a look at this convolution kernel, okay, and consider, say, a toy input image here. Okay, so this input image is just a simple edge, black and white edge. It's white over here, say, and black on the other side of this transition, and it's got noise in it, as you can see, okay? The G function, in this case, is a Gaussian about the input image pixel. So if it was a regular convolution and we took the convolution of this input image against the Gaussian, what would we see? We would average out a lot of this noise, of course, but we would also take that edge and we would blur it very heavily. The F function instead is, okay, remember again, we take the intensity difference. Oh, sorry, it's important to define exactly which pixel position we're talking about here. So the pixel P, let's consider it to be this point over here, which is very close to the edge, but is specifically located on the high side of the edge, on the white side. So the F function in this case is going to do what? It's going to take all of the pixel intensity locations, sorry, all the pixel locations that have an intensity that is close to this reference location at P. In other words, all the values that are close to 1, and it's going to set them high, okay, as you can see here. It's going to take all the pixel intensities that are far away in intensity from P, and it's going to set them to a low value. The final filter kernel is going to be the product of G and F, okay? So it's going to be this weighted, this Gaussian here, but multiplied by this function over here. So this is what's meant by truncation. Okay, it's going to take only this portion of the Gaussian, and this portion over here is going to be set very close to 0. If you take this Gaussian filter and then weight it at that pixel P location, you'll get a value that's high. And if you do this G and F, which is F is going to vary, right, for every different pixel location over here, then you'll end up with a filtered output image that looks like it over here. One way that I encourage you to test your understanding as you review this later is to ask yourself, what would change on this slide if this pixel P here, instead of being on the high side, let's say that it was, you know, at the almost same location, but just on the other side of the edge, what would happen? What would change on this slide if it was down here? And a hint is that this isn't going to change, but this function here is going to change a lot, and this one here is going to change a lot. Okay, so test your understanding later by reviewing that. The bilateral filter of the kernel is going to depend on the image content, okay, as we've looked at. So for example, in this location here where the sky is constant, it's almost all gray, then the Gaussian filter is not going to get modulated by F at all. F is going to be constant and high because all the intensities are the same. So we'll just convolve against, in this local region, against a Gaussian. In this region over here, it's similar to the picture I walked you through in detail on the previous slide. If you look at this image patch here, it's going to be an edge, right? It's white on one side, black on the other side. And the Gaussian filter that's going to apply for that particular pixel at the center of this region here is going to be a Gaussian that looks like this, but it's going to be all 0 over here on this side because these intensity values are very different than the target intensity value at the center. In this textured region over here, something even more complex happens. The reference value at the center here is some kind of relatively bright value, okay? The F function that we looked at before is going to set all of the neighboring pixels here to be, you know, a low value close to 0 if they're dark because they differ in intensity from the reference bright value in the center. And all the bright values are going to be set to a relatively bright, remain a pretty high value. That then is going to be modulated, of course, by the Gaussian G function that we have. And the final filter that we use is shown here. So the output pixel value at the center in this output image is going to be equal to the input pixel values here weighted in a weighted sum pixel by pixel against this weighting function here. So this input image gets transferred to this output image. It blurs, you know, all of the pixel values as you can see here, but it tends to retain and preserve the sharpest edges in this scene. So that's the function, again, of the bilateral filter on another example. Okay. Is another data-driven image processing example, image manipulation by example. I've shown you a couple of examples of data-driven filter functions, the median filter, the bilateral filter, where the value of the filter function, the specific value of the weights that we use, is dependent on the intensity values in the input image. Okay, very unlike convolution. Convolution doesn't operate that way. Here's another example that drives this to an even more extreme. This is denoising with something called non-local means. I always found non-local means to be kind of a bit hard to remember conceptually. You could think of it as non-local averaging. Okay, I think maybe averaging is a better word or a more descriptive, evocative word here. Non-local averaging. What does that mean? So in the output image, instead of averaging over just the pixels that are nearby to it, so for example, for this P here, instead of averaging over the pixels in this local neighborhood, what you can imagine doing is searching over this entire image for other pixels and neighborhoods, rather, that look kind of like this local neighborhood, and using their intensity values or their data values in order to help this this averaging as well. That's what's meant by non-local, not only local to P, but everywhere in the image, and averaging based on similarity of the neighborhoods. So in this picture example here, you can see that P has a neighborhood that looks like high intensity values on one side on the left, low intensity values on the right-hand side. You can see that qualitatively speaking, that looks kind of like the neighborhood at Q1 and Q2 as well. It doesn't look very much like the neighborhood at this pixel location Q3, right, which is much more complex in its structure. So the idea is, if you could take conceptually, if you could take or calculate the output pixel value at P by averaging not just the neighborhood of P, but averaging over in some way all of the neighborhoods of this input image that have similar looking pixel neighborhoods, that would be the idea to do. You can probably guess that's going to be pretty expensive to calculate, maybe even non-trivial algorithmically to express or to write down an algorithm for that. But that's the high level idea of what we want to accomplish. Okay. So this is an example of the mathematics that could be used in order to express what I described, at the intuitive level just before with respect to that image. Okay, so non-local means averaging for image I at position P can be described as a search for Q as an element of, let me sort of resituate myself here. Oh yeah, okay, so all points in this, so S of P is all points in a search region about P. So in some large search region around P, we want to find, consider all points Q inside that search region. And then we weight by P, we calculate a weight that's got input parameter values of both P and Q times the image at that Q location. And this function W with input parameters P and Q is equal to this thing over here, where the key is that the neighborhood around P minus the neighborhood around Q, as you can see visualized here P and Q, the neighborhood around them, or the mean difference between them, is put into this Gaussian function. Okay, so we take the similarity between the neighborhoods in the neighborhoods MP and NQ, and take them, that's what's being calculated in this weighting function of W at positions P and Q. Okay, so that's a way to sort of describe what's going on in non-local means, or mathematically in non-local means. This can be applied, or very similar ideas can be applied in texture synthesis. So in this example, you get an input low resolution texture image, say this source texture value here, and you might want to generate a high resolution output texture image that appears like the input. Well, one way to do that is just to tile it. We've seen versions of this, right, in early versions of our computing devices. And it doesn't look very convincing. It doesn't look like a texture that's large, that's similar to this one. It just looks like a tiled version of that visually. Instead, you can apply something that uses some of the ideas around neighborhood similarity, similar to non-local means. And you could say, hey, look, the main idea is that for a given pixel P, I want to find a probability distribution function for possible values of P in the output based on its neighboring pixels in the source texture input. And we could define the neighborhood n sub P to be like the n by n pixels around P, okay? Very similar to exactly the same as in the non-local means example. So to synthesize each pixel P in the output, say, for example, this one right here in the growing texture that we're synthesizing, we can find other n by n picture. First of all, we find n sub P in the thing that we're growing, and we can find patches n sub Q for other locations Q in the source texture that are most similar to n sub P. So we've organically grown, in this case, n sub P texture that has, as you can see, a bit of grouting here and this line here. And what we want to do is search in the source for other Q locations, as you can see, candidates here, that match or are similar or close to that structure, for, at least for the pixels that have been already calculated. If we do that, then we can sample, we can choose somewhat randomly in optimizing this Q location, and then we copy the next value into that location P. Not the entire neighborhood, but just the next pixel value from one of these candidate n sub Q neighborhoods over here. If we keep applying that same algorithm pixel by pixel on the boundary of this growing synthesized texture, turns out that this is a great algorithm, turns into a great algorithm for texture synthesis. Here are the source input textures, as you can see on the left-hand side here. So these small three things here. And what's shown over here from left to right is this synthesis algorithm where the size of the neighborhood search window, right? So that n sub P, how big is the n by n pixel? So it's 5 by 5 in this case, 11 by 11, 15 by 15, and 23 by 23 in this case. And what you can see is that from this very small source texture, if it's too small search neighborhood, it sort of doesn't pick up entirely on the structure of this small circles here. So it gets broken up a little bit. But as soon as we arrive at a large enough search neighborhood, say 11 by 11, this is a texture that's synthesized that I think we can all agree is a random texture that has a lot of the characteristics of this sample texture here. If you want it to be a little bit more similar to this input, a little bit more similar to like a repeating texture, you can increase the size of the search neighborhood. As you can see here, it becomes more and more similar to the input source texture. But even for these smaller neighborhoods, you get a lot of that self-similarity already, and it generates very convincing looking textures. Here's more examples. This little source texture generating a large wood texture here, compared to, for example, the naive texture tiling solution you can see on the right here. Or you can even take text and just randomly generate texture. It looks like text. Of course, if you try to read it, it's semantically meaningless. But this is an example of a data-driven image processing methodology in application in texture synthesis. In fact, it's got some great applications. This work is due to our own Professor Alyosha Efros here at Berkeley and some of his very early research. Has great applications. They're really surprising. Okay, if you just take this image here and say, oh, I didn't really want a fountain here, let's just delete it. You can just sort of delete all those pixels, mark it in pink for not decided yet, and then just apply texture synthesis inside this region where the synthesizing texture is just the original image. Okay, so again, you just grow along the boundary applying that algorithm I described on the previous slide. And the completion result is, okay, we deleted that little standing structure here, that bird bath. This is the result. In many cases, it generates extremely convincing looking results. These are examples of early data-driven algorithms in vision or image completion in computer vision. Okay. All right. I'll also mention that this algorithm here for finding corresponding locations in the original image can be very expensive to calculate. But there were fast algorithms that were designed for this that make use of sort of some of the guesses that were found at earlier stages of the guessing process, and then use a randomized sampling of those locations. Without going into the details of it, I can refer you to the patch match algorithm that was published in 2009 if you're interested in that. If you're interested in image processing projects, this patch match can be a really interesting project example to look into. It's a fast randomized algorithm for finding similar patches in the source texture or source image around neighborhoods in the growing output image. Okay. All right. And that is the last slide that we have for today. The usual things to remember for you will be in the class notes. Next time we'll pick up and we'll have a lecture on light field cameras and light field photography. And that's what we got for today. Thanks, folks. Great to see you all. Have a good evening.